Variations of physical vapor deposition. Well, there are different types of techniques that use PVD concepts. They are distinguished by improved or upgraded concepts by the science and engineering design. Look at the flow chart here. PVD is classified in three main concepts, that are, thermal evaporation, sputtering and ion plating. As you can see in the chart here, evaporative deposition, electron beam or EBT318 and pulsed laser deposition or PVD is parked under thermal evaporation. Under sputtering PVD, there are 5 techniques mainly utilized to develop a thin film on the sample. The techniques are ion beam, reactive, gas flow, high power impulse magnetron sputtering or high PIMS and high target utilization sputtering or high TUS. The other one of PVD variation is ion plating or IP is a PVD process that is sometimes called ion-assisted deposition, IAD, or ion vapor deposition, IVD, and is a version of vacuum deposition. Now, we will start with the 3 main techniques of PVD. First, thermal evaporation involves heating of the material until it forms a vapor that condenses on a substrate to form a coating. Second, sputtering involves the electrical generation of a plasma between the coating species and the substrate. Third, ion plating, where it is the method that essentially a combination of these 2 processes. What is thermal evaporation? Thermal evaporation is one of the simplest of the PVD techniques. It is the oldest and the most widely used in PVD concept. Basically, material is heated in a vacuum chamber until its surface atoms have sufficient energy to leave the surface. At this point they will traverse the vacuum chamber, at thermal energy that is less than 1 electron volt, and coat a substrate positioned above the evaporating material. Average working distances are 200 mm to 1 meter. An atom evaporating from a source travels in a straight line, thus the process is line of sight limited, and coating around corners or reentrant angles is not possible without substrate manipulation. Thermal evaporation occurs in a high vacuum of 0.1 to 10 MPa. The pressure in the chamber must be below the point where the mean free path is longer than the distance between evaporation source and the substrate. The mean free path is the average distance an atom or molecule can travel in a vacuum chamber before it collides with another particle, thereby disturbing its direction to some degree. This is typically 3.0 times 10⁻⁻⁴ torr or lower. The main reason to run at the high end of the pressure range is to allow an ion beam source to be employed simultaneously for film densification or other property modification. As a result of its simplicity, the cost of equipment ownership is also somewhat lower. Aluminum and chromium coatings for automotive trim are the largest application of this process. Hard coatings of chromium and alumina are deposited on steel or tungsten carbide tools. There are 3 methods of thermal evaporation, that are evaporative deposition, electron beam physical vapor deposition and pulsed laser deposition. In evaporation deposition, a metal source is heated to a high vapor pressure in a vacuum chamber either by passing a current through a electrically resistive heating, normally, tungsten materials container, or by focusing an electron beam on the metal surface. As metal atoms evaporate, they form a vapor that condenses on the cooler surface of the wafer to form a layer. Electron beam physical vapor deposition, or EBT318, is a form of physical vapor deposition in which a target anode is bombarded with an electron beam given off by a charged tungsten filament under high vacuum. The electron beam causes atoms from the target to transform into the gaseous phase. These atoms then precipitate into solid form, coating everything in the vacuum chamber, within line of sight, with a thin layer of the anode material. See the figure here. The picture shows the EBT318 thermal barrier coating on high-pressure turbine blade for aircraft engine. EBT318 is also widely used in the gas turbine industry. It applied to MCRALY metallic coatings as bond coat on turbine blades. If you read about the development about turbine blades, you will find that the major improvement on turbine blade material technology was the development of thermal barrier coatings or TBC. Where directional solidification and single crystal production developments improved creep and fatigue resistance, TBC also improved corrosion and oxidation resistance, both of which became greater concerns as temperatures increased. The first TBC, applied in the 1970s, using an aluminide coatings. Improved ceramic coatings became available in the 1980s. These coatings increased turbine blade temperature capability by about certain 100 degrees C. The coatings also improved blade life, almost doubling the life of turbine blades in some cases.
Pulsed laser deposition is a PVD technique where a high-power pulsed laser beam is focused inside a vacuum chamber to strike and melt a target of the material to be converted in vapor for deposition.
Pulsed laser deposition (PLD) is a physical vapor deposition (PVD) technique where a high-power pulsed laser beam is focused inside a vacuum chamber to strike a target of the material that is to be deposited. This material is vaporized from the target in a plasma plumb which deposits it as a thin film on a substrate, such as a silicon wafer. This process can occur in ultra-high vacuum or in the presence of background gas. When the laser pulse is absorbed by the target, energy is first converted to electronic excitation and then into thermal, chemical, and mechanical energy, resulting in evaporation, ablation, plasma formation, and even exfoliation. The ejected species expand into the surrounding vacuum in the form of a plumb containing many energetic species, including atoms, molecules, electrons, ion clusters, particulates, and molten globules before depositing on the typically hot substrate.